Hi everybody, here is Dumbo.
He's pretty cute, huh? Thank you. But sadly, you're not going to get to watch a video about Dumbo. We're going to do the chapter 10 review. Ha ha. So we're going to be doing a really, really quick review of chapter 10. I'm not going to go into a whole lot of detail on these because you have access to all of the previous instruction, right? You can just go back and re-watch videos for things that you're struggling with. What I'm going to do is just give you kind of a really quick overview of, remember, these are the things that you talked about, and these are the types of things that are going to be on the test. So this is straight out of the book. I just copied it out so we can look at it. If I've got 10-1, we started out looking at composite functions, f of g of x, right, by being able to plug in one function into another. That was one of the first things that we looked at. The next thing was we wanted to look at one-to-one functions, right? Is something one-to-one? And so first it had to be a function and pass that vertical line test. Oops, sorry. Then we had to see, is it horizontal? Does that horizontal line, well, hold on, why are you stuck? Unfold it and wrap it around. What? Okay, here we go. We're not stuck anymore. There we go. Sorry. So one-to-one functions are functions that have inverses, right? Being able to find an inverse is we rewrite it instead of f of x is equal to, say, x squared minus 2. We say y is equal to x squared minus 2, and then we switch our x and y, right? So not y anymore, but then x is equal to y squared minus 2, and then I would solve it for y. Right? That's how we go back and figure those out. Okay? And there's instructions on there too. Remember, there's also those other videos. I'll link them in Classroom, but they're always on Planbook. You can always just go back and look at the previous videos. The next thing that we did was we graphed these things, right? We were able to graph them, see what they looked like. We would plug in values. We would notice that it went down on this side. It had that nice asymptote along the x-axis, right? If my a is a big number, so if it's bigger than, if it's bigger than 1, then it's going to be raising up like this. If it's less than 1, so let's say that my multiplier is 1/2, then it's going to be decreasing as it goes on. We looked at all of those. We also looked at, this is where e showed up the first time, right? That natural number. And so all that it is it's just a base. It's treat it like another base. Everything works the same way. We looked at our two compound interest equations. We had the first one where we've got P times 1 plus R over N to the NT. P is my amount invested. R is my rate per year. And then T is the number of years. N is the number of times compounded per year. If I'm dealing with continuous compounding, then I use E because that's whenever we have any type of compounding that is continuous, or continuous growth, continuous decay, we're dealing with E. They give us another equation. I didn't really go over it because it's the exact same equation, except for instead of a P, they throw in an A sub O. So that's an initial amount. Same thing though. Okay? As I said, you can go back and look at those examples. I've got lots of them that I've done, and if you need any more, just let me know, but I would rather you look at the previous videos to give you an idea. The next thing that we looked at, we looked at logs for the first time, right? And when we were graphing those things, we noticed that they looked very similar to exponentials, except for this. So I can get them at the same spot here. Right? An exponential goes up, right? A log has an asymptote here, and then it still is increasing, but very, very slowly, just like here it's decreasing very slowly, right? I don't think I did. I'm not going to do that right now. Thank you. This one, where my base is a fraction, it's decreasing. Here, it's very similar, right? It works very similarly, it just is a reflection, okay? So instead of going bonk, it's going bonk. Instead of going donk, it's going donk, right? That probably did not make much sense. We looked at being able to switch those things around. I don't have any examples of those right here, but I do want to look at that real quick. So if I've got 2 to the, not n, what am I doing n? 2 to the x is equal to 19. If I want to write that as a logarithm, right, I've got to start here and then work my way around. So log base 2 of 19 is equal to x, right? Remember, you start at your base. The base of your exponent is the base of your log, so log base 2, and then you wrap around, you always end with your exponent. I will also ask you to do things like take a log 12 of x equals 3, and I will tell you to put it into that exponential form, so you're going to have to wrap it around again, right? So that would be 12 cubed is equal to x. Your base, your exponent is equal to a number, okay? That's the main thing that we looked at with those, at least in 10.3, and that was 10.3. The next one was properties of logs, and this has got a nice little graph, or a nice little table here with all of them in one spot, right? Log base a of 1 is 0, right? Anything to the 0 power gives you 1. Remember, if I'm dealing with ln is just log base e. That's all that it is. It looks like it's something much more complicated to deal with. It's just log base e. That's all that it is. So if I have an ln, you can just rewrite it as log base e to help it be a little bit easier for you to deal with. Okay? So we looked at if I've got log base a of 1, that's always going to be 0. Log base a of a, what exponent is going to give you itself? Well, that's going to be a 1. Right? Inverse properties, they can undo each other. Same thing with your natural logs. They have 2 different columns here, but you'll notice the columns are exactly the same. You could, anytime that you have an ln, you could just replace it with a log base e. So if I'm looking at this, ln e to the x, that's like log base e of e to the x. Notice it's the exact same thing, except for an a, you've got an e. That's the only difference. Here, you're looking at the product property. If I've got 2 things multiplied together, I can add those logs. If I've got division, I can subtract my logs. If I've got a power, I can bring that power down out in front. And so the problems that you would work on for things like this, where did they go? Well, I don't have them, but let me make one up. If I had log base 2 of 3x, right? I can separate this out. They're multiplied together, so I can separate them out into log base 2 of 3 plus log base 2 of x, right? We did a lot of practice using those in 10.4. The next one is change of base, and that was where, like, let's say I had log base 2 of 19, that example that we just looked at. If I want to plug that into my calculator, I need to take log 19 divided by log 2, right? Remember, if there's no base, there's that invisible base 10, and that's the automatic base that your calculator will do, okay? The last part was for 10.5 was just going back and solving these things. So you're using your properties, you're using the same relationships that you've looked at before. You're still looking at the same equations and examples. Everything is pretty much the same. You're just working a little bit harder. So instead of, say, taking something like this, log base 12 of x equals 3, instead of just getting it into this form, getting that x out of there, so 12 cubed equals x, well, I know what 12 cubed is. Well, I don't, but I will in a minute. So then x is equal to 1,728, right? So you're going to be using those properties to help you solve if you end up with yucky ones, right? Remember, this is section 10.5. I've got a whole nother video on it, so hopefully it should be all that you need. If you need anything else, let me know. And I miss the heck out of you guys. Adios.